Okay, welcome to Academic Digest class. The question says the period of vibration T of a liquid drop depends on the density, radius, and surface tension of the liquid. Use dimensional analysis to deduce an expression for the dependence of the period of vibration of a liquid drop on these three quantities. Remember, I told you once upon a time that anytime you're asked to use dimensional analysis, that the first method simply states that the dependence, which is T in this case, is equal to the product of the variables, and the variables given here is density, radius, is equal to the product of the variables, surface tension. So is equals to the product directly proportional to the product of the variables. The dependence is directly proportional to the product of the variables raised to unknown power. Let's say this is raised to power unknown power x, y, z. But notice that in this case, when we introduce a quality sign, we always introduce a proportionality constant. So if I know this, I can start working. So T here is equals to K, and I know that density is the same thing as saying mass over volume. And volume is, remember that dimension is simply the measurement of quantities, physical quantities, using mass, length, and time. So I use L. Volume is mass over, density is mass over volume, and volume is liter. L is the length, sorry. L is the dimension there, raised to power 3. So all raised to power x. Radius is represented with L raised to power y. Then surface tension. Surface tension is the same thing as saying force over length. So it's the ratio of force to length. So I have force is mlt minus 2 all over L, all raised to power z. So notice that quickly this and this will cancel. So I'm having T is equals to K M L. Applying law of indices, when this power comes up, it becomes minus 3. So all raised to power x, then L raised to power y, then mt. Notice that if you apply law of indices, the distributive power law, this z will distribute on m and t. So m raised to power z minus 2 raised to power z. Alright, so if we still apply law of indices this time around, the product law. Okay, let's get through with the distributive. X go to m, so mx, l raised to power minus 3x. So we have l raised to power y, we have m raised to power z, t raised to power minus 2z. So at this juncture, we can apply multiplication power law. So if we apply multiplication law, get all the m's together, then the law states that if the bases are the same, add the power. So this is going to be mx plus z, l raised to power minus 3x plus y, then t is on its own. So at this junction, we'll apply the second law of dimensional analysis, and the second law of dimensional analysis states that we must have mass, length, and time on both left hand side and right hand side. So since I don't have it, I know that m into raised to power 0 is 1, l raised to power 0 1. So if I say m raised to power 0 is set as 1 times 1 times 2 raised to power 1, which is the same thing as this. Anything standing on its own is raised to the power of 1. So if I do this, I'm going to have equals to then I will apply indices, equating the powers. Indices, the base law states that if the bases are the same, the powers are equal. So applying that law for m, now you can see that it's going to be 0 equals to x plus z. Then for L is going to be 0 equals to minus 3x plus y. Then for T is going to be 1 equals to minus 2z. So trying to make z subject of the formula, we divide both sides by minus 2. So that, yes, so that our z is now minus 1 over 2. So let's come to m and put it. So this is now the sentence as saying 0 is equals to x minus 1 over 2. So making x subject of the formula, this will cross the equality sign so that x is equals to 1 over 2. So for L to find y now, all we simply need to do, so notice we've gotten t and we've gotten x. That is, we've gotten x and we've gotten z. So let's get L. So clearly you see that to get L, all we need to do is to simply say 0 is equals to minus 3x plus, I will know that y, we've gotten y, have we gotten y? Okay, sorry, we've not gotten y, but we've gotten x. X is half. So let's say I put 1 over 2 for x here. Okay, so notice that we've gotten x, and when for L we have 0 equals to minus 3x plus y. So let's do minus 3x now, replace it with 1 over 2 plus y. So this is now the sentence as saying 0 is equals to minus 3 over 2 plus y. So you see clearly that this will now be the sentence as saying anytime you have a fraction and that fraction is to be added with a particular whole number, you must first do it by using LCM method. So this is the sentence as saying over 2. So 2 here to get out, so this becomes minus 3 plus 2y. Yes, so you can see now equals to 0, and anything standing on its own is over 1. So cross multiply, or you say multiply both sides by 2, so that this becomes 0 equals to minus 3 plus 2y. And if minus 3 cross equality sign, becomes 3 equals to 2y, dividing both sides by the coefficient of y, which is 2. So y is equals to 3 over 2. So with this we've been able to get x to be equals to half, y to be equals to 3 over 2, and z to be equals to minus 1 over 2. So since we've gotten this, we can't leave our answer at this point. We must go back to that equation, the relation, and then try to substitute our value. So remember that the dependence is t equals to, using the first law, k density s to x, radius raised to y, surface tension raised to z. So let's replace this now, so that t is equals to k density raised to power 1 over 2, r raised to power 3 over 2, and surface tension raised to power minus 1 over 2. Applying indices, this will be k root p, then root r raised to power 3, then this will be, applying negative power law, this will be 1 over root. So if we know this will now be the sentence as having this to be the sentence as saying k into root p r3 all over root surface tension. So T is simply equals to k root pr³ all over surface tension. So this is our final answer. This is our final answer. This is our final answer.